Okay, we're ready to start a chapter on gases. In this chapter, we're going to examine gases from every possible angle. If you've had any chemistry in your background, maybe in high school, you're probably familiar with PV equals nRT. That is an equation that students kind of get a hold of and they can remember easily and work with without a whole lot of trouble. So I don't anticipate this to be a really hard chapter for anybody, but we'll see, won't we? Okay, so there is, to begin with, section 5.2, we're talking about pressure. In this section, I want you to actually read it. You're reading 5.2. Take notes and bring those notes to class with you. You're going to be learning about what pressure is and how we obtain pressure when we talk about the pressure of a gas. And we're going to, of course, you see that it's force over area. So you're going to be looking at that. You're going to be looking at the units of pressure, atmosphere, torr, millimeters of mercury, and the relationship between those. So you make sure you bring that to class with you so that you can use it. Now don't move on to what we'll talk next. You need to kind of stop the video here. Don't move on until you've read through that, because we need a little bit of an understanding of what pressure is before we can use it properly in our calculations. Okay, so what we're going to do is we've got 3 gas laws that we're going to be looking at, and the first one we're going to look at is going to be Boyle's Law. But all of these gas laws, whether it's Boyle's Law or the other 2 that we'll cover, basically do the same thing, okay? All of them are called simple gas laws, okay? And Boyle's Law is one of them. There are 4, it says here, 4 easily measured units for a gas. You can measure how much container it takes up. What's its volume? That's easy. Everybody understands volume. You can measure the temperature of that gas. You can know its temperature. Now that you have read about pressure, you have a feel for what pressure is. This is a very measurable quantity about a gas. And the last thing is the number of moles in that gas. How much matter is there in terms of number? And we use N as abbreviation for moles when we're dealing with this equations and the equations that we're going to see here. So those are the 4. In all of the laws, what we do is we hold 2, so underline 2. 2 of those 4 variables we're going to hold constant. So we're undergo a change, holding 2 of them constant, and then see how the other 2 affect each other. So we'll start manipulating the other 2, one of them or the other, and see how that manipulation affects the one left over. The first one is Boyle's Law. And in Boyle's Law, we're going to be focusing on volume and pressure. So how much volume the gas has and what is the measured pressure within the container. So what's being held constant? The T is being held constant, the temperature, and the number of moles is being held constant. Now, lots of different ways that you can hold the number of moles constant, but what you need is a container of some variety, okay? Whether it's a box, whether it's a balloon, you've got to have a sealed container, and in that container are a certain number of moles of gas. And you hold that, allow changes to take place, while in this case you're holding the temperature as well constant. So in Boyle's Law, we need to have a fixed container, we need to hold the temperature constant, and then we're going to see how volume and pressure are related to each other. Okay, so what we're going to do at this point is we're going to break away from this and look at a demonstration of Boyle's Law. So we're going to look at a demonstration of Boyle's Law. What we have here is Boyle's Law apparatus, and what I want you to do is I want you to watch what I'm doing and trying to see the relationship between volume and pressure. Now, what I have here is a little plunger, and it's got a tube that connects over to this pressure gauge, and we can measure pressure. It doesn't tell me what these pressure units are. It doesn't matter. We're just going to be able to see how the pressure changes. There's a certain amount of volume inside of this container, okay, and I'm going to increase the volume by pulling down on this plunger. As I pull down, you're going to be looking at how the pressure changes. Now, we could actually do measurements where we're putting down volumes and putting down pressures, and we could come out with our mathematical expressions. But I'm just wanting you to look at, in general, what is happening to the pressure up here as I increase the volume. So pulling down on the plunger increases the volume, and you are watching the pressure gauge, and you are determining what's happening to the pressure as the volume goes up. Now I'll go the opposite direction. As the volume is going down, you're looking at the pressure gauge, and you are determining exactly what the pressure is doing as the volume goes down. Okay, so you've had an opportunity to look at the demonstration and see the connections as we hold temperature and number of moles constant. What happened when we changed the volume? What happened to the pressure? Now, which one was it? Would you say that they are directly proportional or inversely proportional? Let's talk a little bit about that language, okay? What does directly proportional mean? Directly proportional means as one goes up, the other one goes up right along with it. That's directly proportional. When things are directly proportional, they will have a graph that looks like this, okay? As one goes up, the other one goes up the same in a nice linear fashion. Inversely proportional means as one goes up, the other one goes down, okay? So that would be inversely proportional. Think about it and choose A or B. Now hopefully you did that and you chose B. It's inversely proportional. As I pulled back on the plunger, the volume went up, the pressure went down, and that is the relationship between those two. Okay. We stated that it's inversely proportional, and this is how you would write that in symbol form. The volume is proportional to 1 over pressure. That is an inverse relationship. As one goes up, the other one goes down, and vice versa. So what we're plotting here, instead of kind of doing it that way, it's actually not a nice linear relationship. It would look like this. This is a linear relationship. It's directly proportional to the inverse, but as one gets bigger, the other one gets smaller. All right, when you have an inequality, you get rid of inequalities by adding a constant, that's K, and that gives it an equal sign. So volume is equal to K times 1 over pressure. And that K is basically a defining of that slope of that line right there. All I've done in this next step is done a rearrangement of terms. So we've got pressure times volume is a constant. What does that mean? That means every time I take a certain gas, I'm not letting the number of moles change, okay? I am not letting the temperature change, and I'm going in there and I'm changing the volume. It's going to change the pressure in such a way that you always get the same number out. So let's look at a picture of that. That's what we have here on the screen, a picture of that. We're putting a 2 kilogram weight on the, and it's causing to push down the piston. Now what's happening there? We have dropped the volume in half. What happened to the pressure? It doubled, and that is an inverse proportionality. And that is Boyle's Law. Now eventually we'll do calculations with this. For now I'm just introducing you to the laws and letting you be familiar with it. Boyle came along and saw that pressure and volume are inversely proportional. Now if you plotted pressure and volume on the X and Y axis, instead of doing like I wrote on the light board, volume and 1 over pressure, you see this is not a linear relationship. It drops down, but it is decreasing as the volume decreases, okay? That is kind of what I drew, except I switched the axes there. 1 over volume and pressure gives you a nice linear relationship. As one goes down, the other one goes up. So you need to be familiar with the graphing relationships of Boyle's Law. Now, let's talk about the name Boyle's Law. I really don't care if you remember it's called Boyle's Law. Boyle would be disappointed if I didn't make you memorize his name associated with his research, I'm sure. But what's important to me is that you understand the relationship, that pressure times volume is a constant. Another way to think about that is the linear relationship that you get by graphing those two in that way. So another way to look at Boyle's law is every time you do pressure times volume, you get a constant. You could write it this way. You undergo a set of conditions where you have P1, V1, a certain pressure and a certain volume. Then you allow the volume to change. You measure how the pressure is at that time, and that product has to equal the same product to begin with. So the P1, V1 equals P2, V2 is my usable form of Boyle's law. Now, I don't want you at this point to memorize that. Put a brakes on any, if you like to work ahead and make flashcards and start memorizing equations that I give you, don't memorize this one yet, okay? I want to teach you how to derive it by only memorizing one equation. And that concludes our discussion of Boyle's law.